My name is Alice Tran, and Justin Kim and I will be presenting an RU project funded by the National Science Foundation. We completed this under the guidance of Dr. Michelle Hummel and Dr. Byung-Sung Choi. This project explores a potential method to improve local air quality monitoring and prediction using particulate matter 2.5 data recorded from satellite. PM 2.5 has multiple negative effects on a population's health, and therefore careful monitoring of it is necessary to keep individuals safe. Having accurate predictions of PM 2.5 would greatly improve public health decision-making, but developing these models is still a work in progress. The EPA currently has ground-level PM 2.5 measuring stations, referred to as SLAMs, which provide monitoring at a coarse resolution since the stations are geographically spread out. Recently, NASA has also published the Tempo ABI data, we'll just refer to this as Tempo, which recorded measurements of surface PM 2.5 concentration. The measurements were taken using the Tempo and ABI instruments mounted on satellites centered over the U.S. The potential for this dataset is to improve spatial coverage for air quality monitoring where SLAMs is lacking. Figure 1 is a snapshot of the Tempo PM 2.5 measurements with the magenta markers pinpointing existing SLAM stations in Texas. Our goals are to assess the accuracy of this new Tempo dataset by comparison to SLAM's data in Texas. We can develop a bias correction model and an uncertainty model to address systemic and random error in the data. This also prepares the data for use in spatial temporal air quality prediction models. Figure 2 presents our process and potential future work. We started by collecting the two datasets for PM 2.5 available online. Then we cleaned the data and clipped it to Texas. We matched proximal Tempo and SLAM's measurements, and after this, we're able to visualize the data, compare it by site and hour, and develop the bias correction and uncertainty models. These models can be implemented in multimodal data fusion to aid probabilistic spatial temporal PM 2.5 prediction. Now I'll let Justin take us through our results.
From Figure 2's flowchart, we first take a look at the hourly comparison based on ground level site coordinates between a specific air monitoring site and Tempo data in Figure 3. A site in Austin, Texas was selected for an hourly PM 2.5 comparison between SLAMs and Tempo data. Looking at Figure 3, gaps and spikes are visually present within the data for the month of August 2023. Limitations for SLAMs data is that negative measurements are not filtered out, leading to underreporting. Limitations for Tempo data is that its measurements are limited to daylight hours, measuring the amount of sunlight absorbed by aerosols present within the atmosphere. As a result, the data comparison takes place during daylight hours. Cloud cover also influences Tempo data, either omitting a pixel from spatial coverage due to its excessive cloud fraction or exaggerating measurements, especially if the pixel is located on the edges of cloud cover. Moving down to Figure 4, we have the overall normalized root mean square error, or NRMSE, for coordinates based on major metropolitan areas in Texas. The hourly PM 2.5 NRMSE is particularly higher closer to nighttime due to the dissipation of sunlight Tempo primarily utilizes for data collection. For the plots in Figure 4, the dashed black line represents a target NRMSE of 30% or lower, defined by the Environmental Protection Agency, or EPA, for air quality monitoring systems. Next, we move on to the bias correction and prediction uncertainty models, represented by Figures 5 and 6. The bias correction model from Figure 5 aims to reduce the overall error from the comparison of SLAMs to Tempo data. The prediction uncertainty model from Figure 6 provides a measure of confidence from the overall reliability of predictions. Both of these models are essential for multimodal data fusion, which will be useful for probabilistic spatial temporal prediction for PM 2.5 in future work. In conclusion, the NRMSE resulting directly from SLAMs and Tempo exceeds the EPA's target error of 30%. The bias correction and uncertainty models allow for correction and prediction of random and systemic errors within PM 2.5 data, which is a necessary step for integration into multimodal data fusion models. With this integration, a broader spatial coverage of air quality monitoring can be utilized by officials and citizens to take better mitigation measures to reduce health-related impacts during severe pollution events. Thank you for listening to our presentation.